Hello everybody and welcome to this lecture. In the previous lecture we learned how to create functions, and in this lecture it's going to be rather quick, but we're going to learn recursion with user-defined functions. Now recursion is basically being able to call a function that we defined within that function. So before we created our first function, and when we did that we simply just returned something. But now when we do recursion, we're typically going to be returning an instance of the same function. So just as an example, we had our first function here, and what it can do, we're basically telling it to return first function. Now we're not going to want to do that because we'll just get stuck in an infinite loop, but I've got 3 examples prepared which are classic recursion examples, and I'll be comparing them against non-recursive function calls. So you can pretty much do recursion even without doing recursion. So a certain function can be implemented both recursively and non-recursively. So a very classic example is doing a factorial. Now if you don't know what a factorial is, it's denoted by x and then an exclamation point. In that, it's pretty much telling us it's going to do x times x minus 1 times x minus 2 all the way up to x minus n, where n is equal to the value before 0. So if we had, for example, we did 5 factorial, that would be equal to 5 times 4 times 3 times 2 times 1. So you would get 5 times 4, that's 20, times 3 is 60, times 2 is 120, and then of course times 1 is itself. So let's show you the non-recursive way first. So we're going to create a function out of this. So I'm going to say function, and then we're just going to call it factorial. You can name it whatever you want. And then the parameter it's going to take in is x. So like I said before, a factorial is denoted by x exclamation point. So the parameter we're passing in is that x within that x exclamation point denotion. So to do a factorial non-recursively, we need to start off with some base number. We can't start off with 0, because then if we multiply that by the next number in the series, you're going to get 0 up to x times. So what we're going to do, we're going to set a variable called y, and we're going to set it equal to 1. Now basically all we need to do is we need to loop through. So we're going to use a for loop, and we're going to loop from 1 to x, and it's going to be inclusive, so we're going to use less than or equal to. So I'm just going to say for I equals 1, and then I is less than or equal to x, and I'm going to increment that by 1. And now all we need to do, we need to multiply I to y. So y, and remember we learned times equals I. So this will tell us it's going to start off at 1, and then 1 times 1 is of course 1. So now we have 1 times 2. So that's 2. Now we have 2 times 3, which is 6. And then 6 times 4, which is 24. And then 24 times 5 should give us 120. So in the end, we just return y. And like we did with the functions we created the other day, we can just echo factorial, and so we'll do 5. So let's go ahead and save this. And then I'll go into the browser. And you can see we get the answer 120. So what if we did 6? So 6 is basically 6 times the factorial of 5. And oops, I didn't save that. And then if we refresh, you get 720. 6 times 120 is, of course, 720. You're probably going to, if you're wanting to go a really high factorial, you're going to want to stick to this non-recursive way. So, say we did 50. We'll get a nice big number, 3 times 10 to the 64th. So, 50 is kind of big. Let's try 20. 20, still huge. 10, it's not that big. It's still a large number. But now, let's show you how we can do this recursively. So, I'm just going to I'm going to set 10 back to 5 here. And then I'm going to get rid of the code within our factorial function there. Now, we're going to be decreasing x by 1 each time. So we want to have a base case. We want to check to see if is x less than or equal to 1. So if it's less than or equal to 1, we just want to return 1. Because if it gets down to 0, then we're going to get 0 as our final answer, because 0 times anything is 0. So we'll just check. If x is less than or equal to 1, return 1. Awesome. So now we're not going to get anything. We're going to get a blank screen because we haven't done any recursive call just yet. So in order to make this recursive, we're going to have to return the function that we just made, factorial. So we're going to want to return factorial of x minus 1 though, since we want to go by 1. But all this is going to do, it's just going to return x minus 1 until it gets to 1. So if we were to refresh this, we're just going to get 1 and not the 100 that we're expecting. So in order to make this correct, we need to multiply x by that factorial call of x minus 1. So you can see we condensed the code just a little bit. We went from, let's see, 1, 2, 3, 4, 5. It's about the same length, maybe one line less. But this is how it becomes recursive. So now that we have returned the value of x times the returned value of factorial x minus 1 up until 1, we should get 120 now. Now if we were to try a larger number, say 50, you're going to have these 50 recursive calls. But until you start dealing with really, really large numbers, you're not going to really worry about speed at this point. So if we went to 100, we might break it. Yeah, just because we can't. You can see this is an error in my PHP. The maximum function nesting level 100. So if we tried 99, let's try 98. You're going to get this huge number, 9 times 10 to the 153rd power. So if you want to compute really, really large factorials, either way, you're going to get about the same speed between a recursive and a non-recursive call. Now, an even more classic recursive function we have is a Fibonacci sequence. The Fibonacci sequence is basically the sum of the current position minus 2 and the current position minus 1. So we start off with 1, 1 basically. And so now we're at this position x. So x minus 2, then we're left with 1 plus x minus 1, which is also 1. So 2. And then say we want to go to the next one. So now we just go back 2 spaces and then add that to the space right behind it. So now we get 3, and 5, 8, 13, etc. So how would we do this non-recursively? So I'm going to create a function here. I'm just going to call it fib. And then I'm just going to input the x value we're going to use. And that's going to tell us to go how many places within the Fibonacci sequence. Now the recursive way to do this is going to be a lot cleaner, but since we're doing this non-recursively, it's going to be a little more tricky to figure out. what we need to do first, we need to set a few variables that we can change later on when we loop through x. So the first one, we're going to do the previous value. So we're going to say this variable called previous, or prev, and we're going to set it to -1. That way, so when we combine it with the first result, we're going to get 0. So then, another variable, we're going to call it result. This is the result we're going to return in the end, and we're going to set this to 1. You'll see why we have -1 and 1 in a second. And then last but not least is sum, and sum is going to keep track of these two values that we're swapping through, n-1 and n-2. So now after we have that, we want to loop through x, starting at 0 though. So for I is equal to 0, and we're going to say I is less than or equal to x as well, and then increment it by 1. And now we're gonna reset these three variables that we just created. Now, the position that we're currently at is n. So our new sum is going to be the position from n-2 plus n-1. So sum is just going to be equal to the previous times the result. And now we're gonna be swapping values here. We're going to set the previous equal to the result, and then we're going to set the result equal to the sum. So this is our new n. And then in the end, we just return result. And like before, we can echo fib, and we'll do 5 as well. Actually, let's do 10. So if we did this correctly, we should get 55. Because if we go down the line, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the 10th is going to be 55, and that's correct. But you can see this is basic. This is 12 lines of code. To make this recursive, so much easier. You'll be surprised. So I got rid of that. I'll post that in lecture notes so you guys don't have to worry about what it exactly was. This is just an example of showing you how recursion works. So now, to make this recursive, like before, we need a base case. And in our case of the Fibonacci sequence, we're going to check if x is less than 2. You can see up here, if it's less than 2, it's going to be 1 no matter what. So we're just going to return 1. And then if x is obviously greater than or equal to 2, we're going to do what we just did with that for loop. We're going to return the Fibonacci number at n-1, but I'm using x in this case, plus the Fibonacci sequence at x-2. So this is making 2 recursive calls in one step. So now if we were to go ahead and echo fib of 10, whoops, less than or equal to 2, 55. Awesome. So that's it condensed into only 6 lines of code. So we literally just shaved off 50% of our code. We saved it, but when we're going to deal with larger numbers, you're going to reach a maximum really quickly because we're having 2 recursive calls in the same function. See, now I'm doing this 50 times, and you can see it's loading. It's taking a while to load because, it's doing 50, and then when it calls that, it's going to go 49 and 48. And then 49 is also going to call 48 and 47, and so on and so forth. So, in a case with larger numbers, you might be better off dealing with the for loop example, the non-recursive way of doing the Fibonacci sequence. Otherwise, you're going to be caught in this big loop. So, we ran out of time. It took 30 seconds just to get to the 35th number. So you can see as it goes down, once it reaches the 18th number, it becomes really slow. 24 seconds at that point. So there's always going to be some case where you're not going to want to use the recursive versus using the non-recursive. So it depends on how many numbers you're expected to do. If you want to save code and you're not going to be using the Fibonacci sequence up to 50, then fine, go ahead and use the recursive call. But if you plan on using really larger numbers, you probably want to stick with the for method, because that's going to do it in constant time. Now, the last example I want to show you is a little more tricky, but it's kind of a combination of trickiness between the last two. This one is the greatest common divisor. So in this one, we're going to input two numbers, and we're going to find the largest number that can divide evenly within both of those numbers. Okay. So I'm going to create the function. I'm going to call it GCD, and it's going to take in two parameters, an x and a y. For now, we're just going to assume that we're going to always get proper values. So as long as one of them is greater than the other. So okay. So how do we do this? We want to find the divisor, so we're going to be dealing with the modulus that we used back in week 1. And we're going to use a while loop. So here we go. We're going to say while y doesn't equal 0. So at the moment y is equal to 0, that means we reached the highest value. And then we're going to create one variable inside of here. It's just going to be a temporary variable, so we can reuse another variable after we change it. So the temporary variable is going to be set to the value of y. And then what we're going to do with y, we're going to do x modulus y. So the new value of y becomes the remainder of x divided by y. And then x is set to temp. And then we can return x in the end. Because when y is equal to 0, x is going to be our last y value. So we can pick two numbers. Let's say, I don't know, 12. Let's do, I don't know, 63 and 12. Let's see if there's a greatest common divisor between the two. 3. Okay. So 63 and 12 can both be divided by 3, which makes sense. And if we did 60, we should get 12, because 60 divided by 12 is an equal 5. So now what if we tried two numbers that don't share a divisor except for one? So let's, I don't know, 291 and 17. I'm just guessing. 291 and 17. They both cannot be divided evenly except for 1. So that's the non-recursive way of doing a greatest common divisor. But you can kind of see where we're going to go when we make this recursive. Like I showed you here, we set x equal to the y we passed in, and then we set y equal to this remainder of x divided by y. So let's go ahead and make this recursive. So how many lines of code? That was 6 lines of code. Okay, let's see how much we can shell down. Okay, so our base case in that case was, when does y equal 0? Okay, so if y, in our case, equals 0, like we did before, we return the value of x. But if y is not equal to 0, then we would just return the greatest common divisor, but we're going to swap around the parameters now. Like before, I had temp is equal to y, and I said x equal to y. So I'm going to send in this new y parameter, or x parameter is equal to y. So the greatest common divisor of y, and, like we had before, x mod y. So now let's go ahead and change this back to 6312 and then refresh. We get 3. So it's working. Let's try 6012. 12. Awesome. And that shaved down 2 lines of code. If you don't include empty spaces, then it shaved down just a little more. Awesome. Now, you really could put this into one line if you really wanted to. I don't believe we might have gone over the ternary operator, but in the case we hadn't, I'm not going to show you in one line. But for the hell of it, I will put that in the lecture notes, and so you guys can try to understand it from there. So this is recursion in a nutshell. Lecture notes, as always, will be in the description. Feel free to post a comment, talk about it on the Google group discussion, post it on Reddit, do whatever you'd like. And I will see you guys next week. Alrighty, goodbye.